Thank you. Thank you very much, Mr. Chairman. And thank you to the studio for this invitation. So I was here all the way back in 2007, 2008, and it's amazing for me to see how the institution has evolved and matured over that time. It's really quite remarkable. Actually, apropos of, let's see, where's the pointer? Where's the pointer on this? No, that advances the slides. Is there a pointer? Oh, yeah. Yeah, I got it. Thank you. I actually added sustainability to my title, maybe anticipating some of these comments. So as was mentioned, I'm going to talk today about actually one of the challenges of a conference like this, which is amazing and wonderful, very broad, very different things, is that we are changing topics typically very quickly. And in fact, I noticed that the word plasma has been used multiple times. Again, Vincent mentioned plasma this morning. So this is a different kind of plasma. It's not blood plasma. It's not membrane plasma. You'll see it's an ionized gas plasma. So what are we talking about here? So plasma in this context, in a gaseous plasma, basically it consists of free electrons and positive ions that are buzzing around in the gas phase. Typically what happens if the density is high enough, the plasma density in sub P is equal to both the electron density, which is very close to the positive ion density, so the gas as a whole is quasi-neutral. Typically you can create plasmas lots of different ways, but the discharges that we use are typically driven by voltage or current sources. You can see this little cartoon here. There's a RF voltage source connected to a couple of electrodes. That creates electric fields. That accelerates electrons. That ionizes the gas. It maintains the plasma. So one of the things that's most interesting about the application that I'll talk about today of plasmas is that they are what we refer to as non-equilibrium plasma. And what we mean by that is that the electron temperature, or I put it in quotes because it's not actually a thermodynamic temperature, the electrons are much hotter than the neutrals, T sub n, which are typically about the same temperature as the positive ions. This has to do with the difference in masses of the species. And as we'll see, this has very profound implications for many different applications. So plasmas are very common. In fact, it's observed that the majority of the visible matter in the universe is in a plasma state. You see this whirlpool galaxy, this false color image here shows plasma emission and magnetic field lines. The aurora borealis in Earth, of course, lightning, which we see very commonly. So all the lightning flashes from our French astronauts talk a couple of days ago. The solar corona, of course, the sun itself is completely ionized. So plasma is very common, not only on Earth, but throughout the universe. But these non-equilibrium plasmas, I argue, they're a unique form of matter. So looking at this little schematic here, there's a chamber shown here. Here's the electrons and ions, positive ions and negative ions. You sustain this thing by applying electromagnetic power of some sort, E fields and B fields. Typically, they'll accelerate the electrons and ionize the neutral molecules. I say here these are weakly ionized gases. Most of the molecules in the chamber are neutral. So those charged particles will go to a wall, they'll recombine, they'll come back in as neutrals, and this whole thing is going around and around. And the point is that because the power is deposited into the charged particles, into the electrons and the ions, they have to have collisions with the other species, the neutral molecules, in order to exchange that energy. And so under many conditions of interest, these species have way too few collisions with each other before they're lost to the walls, or they perhaps will flow out. And so kinetics controls the distribution of energies. You don't have a single temperature at any given point. And because of that, you can manipulate these systems in a variety of different ways and get very, very different results. So say here, as I mentioned again, the electron temperature is much higher than the other species temperature. You can get vibrational temperatures, which are much higher than rotational or translational temperatures. You can get electronically excited states like metastables. There are fast atoms. Positive ions will hit surfaces. It's very important in semiconductor applications, for example. There are photons present. And the whole thing is a very complex system. So let me start by talking about applications in nanofabrication. In the US, there's a renewed emphasis on making chips in the US. Historically, over the last decade or so, the manufacture of integrated circuits, you see a little picture of a wafer here, has been done more in East Asia. But if you look at the scale of this industry, it's really quite remarkable. In terms of annual revenues, the electronics industry as a whole is about $2 trillion per year. The semiconductor industry, which has experienced, as I note here, about 7% of growth per year since 1988, it's on the order of about $500 billion, and it's going up, thought to be close to $1 trillion by the end of the decade. So to make semiconductors, you need a lot of sophisticated equipment, the wafer fab equipment. That's an industry that's about $50 billion per year. And plasma equipment, which I'll talk about today, is a substantial portion of that industry. So many of you may not know much about how integrated circuits are made. This little cartoon gives you some idea. Basically, it's called planar subtractive processing. One begins with a substrate, maybe it's a silicon wafer. You deposit a film like aluminum or polycrystalline silicon. The next step is to deposit a material called a photoresist, which is sensitive to light. Then there's a photomask with a pattern in it, and you want to transfer that pattern into the underlying film. So the light will pass through certain parts of the mask, but not others. That changes chemically the photoresist in certain locations. You can wash that away after development. And then you use some kind of an etching technique, for example, with plasma, to remove the part of the film that's exposed here. And after that, you can remove the photoresist. And now you notice the pattern of the film is the same as the pattern in the the photomask. And this is done many, many times over the surface of the wafer. And this is how these patterns are developed. Now, it turns out, you'll notice here in this little cartoon, the film has been etched perfectly anisotropically. This is a characteristic of plasmas. You can't do that with liquids. Liquid would tend to undercut the film. And so in the process of making these chips, the transistors smaller and smaller and smaller, this characteristic of plasma etching is really important. So this problem of plasma nanofabrication is really a very interdisciplinary problem. So of course we start with plasma science. I mentioned the electromagnetic fields coupled in. You create electrons, ions, free radicals. There are photons created, lots of excited state neutrals. But a big part of this problem is that the way you control these devices has an almost infinite number of different combinations. I say here 10 to the 20 different combinations of ways of controlling the things like the gas flow, the gas composition, the pressure, the frequency. There's pulsing regimens. There's essentially an infinite number of ways to do this. But of these types of plasmas, we're particularly interested in what's happening, the coupling between the plasma and the gas phase and what's happening at the surface. So you have to worry about the surface properties. There's surface science involved. There's materials characterization. And of course, you're making a device. And so there's device physics. Vincent mentioned earlier quantum materials. Of course, semiconductor devices have been made for decades. Quantum materials, in many cases now, are being made through thin film devices as well. So many of the same technologies are used to make the quantum materials. We engage in things like atomistic simulations of plasma surface interactions. There are plasma diagnostics, plasma modeling, et cetera. So it turns out that although the technology is very widely used in the industry, there's a lot of things we don't understand even qualitatively. Like, for example, how does the plasma create or modify atomic scale defects at the surface? One of the things that's very important in many applications is the surface texture. You can rough it or smooth the surface with the plasma. People don't understand how this works even qualitatively. You generate electron hole pairs in the semiconductors, plasmons, UV light. That's not well understood. How does that change the surface chemistry, for example? The surface composition and structures are very complex. And in general, we're dealing with three-dimensional nanofeatures within which there's transport chemistry, and that's not well understood at all. So I like to say that plasma fabrication or nanofabrication science is really at the interface of the sciences associated with the gas phase plasma and what's happening at the surface. It's highly interdisciplinary. So many of you have heard of the so-called Moore's law. It's not really a law, it's just an observation that Gordon Moore made back in the 60s that, this extrapolate back from 1970, but this is a log plot of the number of transistors per chip as a function of year. If you've seen this sort of plot before. So this ended at 2018. We've continued to go up a little bit. So this is now, they're making on the order of tens of billions of transistors per chip. And what Moore's law basically amounts to is that the industry's been able to shrink the dimensions of the transistors and the interconnects that wires them together. And this has led to this remarkable transformation in computing power per unit cost over several decades. And plasma technology has been an enabling technology. You couldn't do this without the ability to etch these little features at the surface. The thing is that we're basically reaching the point now with over tens of billions of transistors per chip. The question is, what is needed in the future? This has worked very well in the past, the shrinking of the devices, but what's the next step? So I borrowed this slide from Philip Wang, who had been Taiwan Semiconductor Manufacturing Corporation's. He was vice president of corporate research. He's gone back to Stanford a couple of years ago. I'll just quote one of the things he said. I'll just note here. He calls this the elephant in the room. He's using this FinFET. FET stands for field effect transistor. And you can see from the transmission electron micrograph here that you can really actually see the individual atoms in these transistors. It says the fin is slightly less than 10 nanometers. You can actually see the individual atoms, and very soon you'll run out of atoms as this thing continues to shrink. But then he says, on the other hand, this powerful knob that we've been using, by that he means shrinking, is not the only knob we have at our disposal. And what he's talking about is the fact that the industry is turning to many new types of materials, many new types of devices, new packaging schemes, and so on. And so there continue to be major challenges ahead in the industry. So I borrowed this slide from a colleague at Applied Materials who's pointing out that the new types of devices, these new structures that they're imagining, like 3D NAND, 3D DRAM, gate-all-around, 3D packaging, he says vertical processing, horizontal processing, directional processing, selective processing, integrated processing. These are all novel device designs that people are thinking about implementing in practice now. In part, they've already done so. And then he points out the fact that there's a huge growth in new materials adoption from the past to more or less the present, and then looking at the future. He says, in fact, there's trillions of combinatorial options for all these different materials, and every one of these materials represents a processing challenge. We don't have any idea of how to process many of these different materials. And so this is really the frontier in the industry, is to be able to do plasma processing and other kinds of processing with these very novel 3D devices and a lot of new materials. Okay, so I'm going to switch gears here and go away from the semiconductor applications and talk about something that's seemingly very different, although there are some similarities, and that is the use of these plasmas in biomedical applications. So a few years ago, we started looking into this. By the way, I realized that the last time I gave an international talk was actually in this room at the Plasma Cosmetics Conference in 2019. So this brings that to mind. So this is the finger of a former postdoc of mine at Berkeley, and she was using a helium plasma jet device, and we were looking at, she didn't have nail fungus, but this was just for illustration. So it turns out these plasmas can be used for treating toenail fungus. Another application, and I'll talk a bit more about that today, this is a helium plasma jet. This is an argon plasma jet. This is from a team in Greifswald, Germany that I work with, where they use these jets to treat cancerous lesions, head and neck cancer lesions. I'll talk a bit about that. So this is, of course, a huge area. There's a lot of things going on. I just wanted to sort of cut to the chase that one of the things we realized, the community realized, is the reason that these plasmas, one of the main reasons these plasmas are biomedically active is that they create a lot of reactive oxygen and nitrogen. These are very important species in aerobic biology. For example, superoxide, hydrogen peroxide, nitric oxide, et cetera. It's not the only thing that's going on, but we think this is probably one of the major reasons that these plasmas are medically therapeutic, or can be. Now, unlike the plasmas used to etch semiconductors, which are low pressure, I didn't mention that, but they're typically on the order of tens of millitorr, these plasmas, of course, are operated at an atmosphere with a gas temperature that's near room temperature. Otherwise, of course, you would be burning the tissue, and you can avoid that. So sorry about this kind of ugly picture here. This came from a colleague in Greifswald. This was from Hans Robert Mettelmann, with whom we did a little bit of collaboration. This paper came out in 2018. So as I mentioned, Hans looks at head and neck cancer treatments, and they were using a device like this one. In fact, it was precisely this one. It's called the KenPin Med. It was developed in Greifswald. And they're treating these patients with squamous cell carcinoma. Now, I mentioned that Germany has been probably the most ambitious country in the world in investigating this new technology. And the patients that he was allowed to treat in Germany were all terminal patients. They were within a few months of death. And the government agreed to allow the use of the plasma for palliative care. It turns out these lesions become infected with antibiotic-resistant bacteria, and they smell very bad. And so the patient's friends and family typically will not come visit them because of that. They feel very awkward. Plus, they're painful. They actually hurt quite a bit. And, of course, they're life-threatening. So Hans sent me this picture back in 2016 because he was quite excited. One of the patients that he was treating, I think he only had a cohort of 6 in this group, he was actually seeing that the lesion appeared to be healing. Now, it turned out that this guy later experienced a relapse and died. Subsequent clinical tests that they did in Germany of about 30 or 35 patients showed that the plasma treatment was approximately as effective as the best immunotherapies with far fewer side effects. So a huge question in this community has been, and continues to be, what are the possible mechanisms that can explain this? It's actually not clear how the plasma could actually work. And I'll just talk about a few examples here. Actually, I think I'll skip this one in the interest of time. There are a number of mouse studies that were done, of course, before they did the human tests. So I wanted to give a shout out to my friends at GREMI, because the GREMI group at the University of Rhode Island, I think I failed to mention this. This was the group that I collaborated with when I was here in 2007, 2008. So Eric Robert and Jean-Michel Pouvel, both of whom were involved with the Plasma Cosmetic Conference I mentioned, have done a lot of really nice work. I had nothing to do with this. This was far after I left. One of the nice things they did, you can see this so-called plasma jet, plasma gun, sometimes it's referred to. It's a very simple device. So you bring in a rare gas like neon or argon. There's a high voltage inner electrode and then an outer ring, which is grounded. The gas flows through the tube, and then you can see that there's a plume of plasma that leaves the tube. And then, of course, it's hitting whatever you're processing out there. So they were the first to be able to measure the electric field as a function of position down the tube, and it's very similar to the field that the tissue would experience at the tip of this plume. So this is a little bit complicated. Basically, this is the voltage profile over a course of 4 microseconds, and the other plots were the measured radial and axial electric fields as a function of different positions down the tube. And the main thing to look at here is the magnitude of the fields are on the order of 5 to 10 kilovolts per centimeter. And the reason that's important is because those pulsed fields are able to electroporate. And we think that cell membrane electroporation is likely to be one of the mechanisms that's important here. And the GREMI group here at Orléans were the first to really show this clearly. They did another set of experiments. This was actually a little bit earlier in 2014 that I thought was very important. So they did some mouse studies, and again, using a helium plasma jet, which they applied to different locations on the mouse. And with various optical fibers, they were able to measure the subcutaneous blood flow and blood oxygen content at different locations. And this turned out to be really interesting. So this is the O2 content of the blood measured in partial pressure of oxygen. So during the plasma application of about 5 minutes, they saw a remarkable increase in the O2 concentration in the subcutaneous blood, which lasted on the order of tens of minutes, and a corresponding increase in the local blood flow as well. When they applied the plasma to another location, this time for 15 minutes, they saw quite a dramatic increase, again, in the oxygen concentration in blood flow. Now, it's not exactly clear what the implications are for this. What is this doing therapeutically? It's probably having some effect, we think. These effects were later confirmed by other groups. There's some thought that the nitric oxide that plasma is generating, which is known, of course, can dilate blood vessels, may have played a role in this as well, but it's not completely clear. So, in fact, this raises the point of the likely importance of reactive oxygen and nitrogen species. When I started looking into this about 10 years ago, and I found papers like Didon and Tannenbaum's paper looking at white blood cells like neutrophils and macrophages, and realized that these cells are making many of the same reactive species that we make in the plasma. Of course, they're doing it typically with enzymes. In the case of nitric oxide, you're using inducible nitric oxide synthase. Various oxidases are used to make O2 minus. Superoxide dismutase will make hydrogen peroxide. They'll react together. Very important intermediate molecule is peroxynitrite, O minus. We also make peroxynitrate, and these combine in various ways. Here's another little picture that I found from another paper. Of course, nothing to do with plasmas and phagocytes. Here's an NADPH oxidase, which takes NADPH and oxygen and kicks out O2 minus. In the presence of myeloperoxidase, which is this, and hydrogen peroxide, you can make HOCl, which is not Clorox. I think what the author meant was bleach. And that turns out to be a very important way how the phagocytes kill the enclosed bacteria. We can make exactly the same species with plasma. And I used this little sketch of Stefan Reuter, who was at Greifswald for a while. Now he's in Montreal. This is that argon plasma jet that I mentioned earlier. And Stefan is showing the species that actually can come out of the jet that mixes in humid air. The hydrogen peroxide is coming from water vapor, which has been dissociated and recombined as hydrogen peroxide. And then, of course, when they go into the water, into the liquid, adjacent liquid phase, some of the species change. But they're essentially identical to the species that the cells are themselves creating for many of the same purposes. That is for disinfection, for shrinking tumors, et cetera. So the community in plasma medicine is really still struggling with the idea of, well, what's actually going on? What's the plasma really doing? We're pretty sure that these reactive species are playing an important role, but precisely how they do it is not so clear. Okay, so let me switch to the last topic here, which is, apropos to the previous comments, is plasma's use for sustainability. So now I'm going to switch gears and switch scales quite a bit, and talk about one application that we've started since I've come to Princeton, which is to look at the pyrolysis, or the thermal decomposition of natural gas, which is primarily methane, to generate carbon dioxide emission-free hydrogen. That is, if the electricity used is renewable. And it turns out that plasma is a promising technology on large chemical plant scales to pyrolyze natural gas and potentially other applications such as ammonia. You may know that ammonia has been proposed as a hydrogen carrier, but in many cases you're going to want to crack that ammonia, and plasma is a potential way to do that. So, but here's the thing though, if you're going to do natural gas pyrolysis and you want to make globally significant quantities of hydrogen, you're going to make an enormous amount of solid carbon. As I'll mention, if we can make that solid carbon in the form of carbon nanotubes can be spun into carbon fibers. Carbon fibers could potentially be used for other structural applications. So let me just describe a little bit about this. So the advantage of methane pyrolysis as compared to water electrolysis is that it's much less energetically demanding to break the hydrogen off from the carbon to make hydrogen, as opposed to electrolysis. And both of these in comparison, of course, to the way that hydrogen is primarily made today industrially, which is through steam reforming of natural gas with emissions, substantial emissions of carbon dioxide. Now, of course, these emissions are only zero if you're using CO2-free electricity generation. And I might add, you avoid leaks of the methane from the place where you get it to where you're going to process it. And that's a non-trivial thing. But this is a clear motivation. And in fact, there's a plant that has been built, the first plant here by this company, Monolith Materials, outside of Lincoln, Nebraska. It was commissioned in 2020, and now they're in the process of scaling it up. They're basically adding 12 more of these reactors in parallel. So their basic idea is they take the natural gas, they take renewable energy, and they use a plasma process, and they make carbon black. They make carbon black, which they sell to manufacturers of tires and so forth. And they're planning, as I understand it, to use the hydrogen in an adjacent Haber-Bosch plant to make ammonia, which will make fertilizer. And there are some emissions, CO2 equivalent, but it's primarily emission-free. So they've announced that when this full expansion takes place, they'll be using something like 2 million megawatt hours per year of electricity. So these plasma processes take a lot of electricity, which, by the way, is the reason that in the past people have not used plasma in large-scale chemical processing, because you use a lot of electricity. So here's a little schematic from their website. This is their reactor. Natural gas comes in one line. I think they're typically use additional hydrogen. They mix it together. I call this artificial lightning. They use a three-phase AC plasma. By the way, this technology, this three-phase plasma, was significantly advanced by a researcher in Paris, Fulcherry, at École de Mines in Paris. Did a lot of work with these guys. And the idea is that if you do it properly, you can break apart the methane and form carbon in the form of carbon black and hydrogen. But again, if you do this, you're making a huge amount of carbon. I adopted this from Mark von Keats's RPE presentation. So solid carbon from a single quad of hydrogen, it's about 1% of the US consumption, is many millions of metric tons of carbon. So what are you going to do with this? The carbon black market's too small to absorb all this carbon. And so we started working with ExxonMobil at Princeton. They're not interested in the carbon black market, it's too small. And so the answer is to try to make carbon nanotubes. And I'll use this example, this Russian company originally out of Novosibirsk, and they spread around the world. They used a plasma, an arc plasma, and the idea is this arc induces metal evaporation from a molten electrode. As the gas then flows downstream, that metal vapor condenses to form nanoparticles of primarily iron, which acts as a catalyst, which will further decompose the methane and induce the growth of the carbon nanotubes. And it provides a continuous supply. So they're reporting on the order of 80 metric tons per year of fiber-grade carbon nanotubes, which I think is the largest in the world right now. But just to give a little cartoon here, so here's the little iron nanoparticle. One of the keys to this process is making the nanoparticles with a very uniform size distribution of on the order of, I think is about 5 or 6 nanometers. And this is tricky to do. And if you do it properly in the presence of this decomposing methane, you can get the growth of very long carbon nanotubes. This little picture from a recent article from Adam Boyce's group at Cambridge. They weren't using a plasma. The same idea, though. You can make these long tubes, and those can they will adhere to each other, and you can use that to make carbon fibers. So what's the point? So Matteo Pasquale at Rice has done some very nice work in this area. It's pointed out that it's the case today that you can make these high quality, fiber quality carbon nanotubes from pyrolysis converted to fiber sheets, et cetera, that in principle could displace or help displace steel, aluminum, and copper in the future. The problem right now, of course, is that when you make carbon nanotubes this way, it's actually quite expensive, ranging from thousands to hundreds of thousands of dollars per kilogram. So except for specialized applications, you really wouldn't be able to do this. Now, Matteo has pointed out that these costs have dropped by a factor of 1,000 over the last 20 years, and the hope is that if that continues, eventually these carbon-based materials could be used to replace these metals. And I think the goal is to try to get this down to below $10 per kilogram. If that can be achieved, then replacing some of these metals, and for example, mining bauxite and mining copper is environmentally not so great, right? And making steel induces a lot of greenhouse gas emissions as well. And so the hope is that we'd be able to use carbon, not to burn it, but in fact to use it as a structural material in the future. Okay, so let me summarize here. So what I hope I've at least begun to tell you today is that these kinds of non-equilibrium plasmas can be extraordinarily versatile. Lots of different kinds of applications. I haven't talked about a lot of others today. Nanofabrication, the biomedical, therapeutics, and large-scale chemical processing are all in very different stages of development today, but I think they're all very promising for important global applications. And I would like to point out that in the context of the studium, this perhaps is a topic that fits in well with the fact that you need to assemble teams of researchers. In the first example on nanofabrication, I pointed out that you not only need plasma scientists, you need surface scientists, you need material scientists, you need device scientists. And over the course of my career, we've never, in our community, been able to put together those kinds of interdisciplinary teams. And as that industry is moving towards essentially atomic scale precision that's needed, that kind of multidisciplinary team is going to be important. The same thing you can say, certainly in the biomedical area, some of my plasma friends didn't really know, I think, what they were doing very well. And you really need to have, if you're going to be, for example, studying cancer treatment, you need to be working with people who are professionals in cancer. Or if you're doing something in the immune system or whatever it is, you have to have collaborators that are really professionals. And the same thing with large-scale chemical processing. Our collaborators at Exxon know how to build large-scale reactors. Folks in the plasma community have not done that. So you've got to have these teams. And maybe this is ideal for institutions that are inclined and intended to support multidisciplinary activities. Let me just say one last thing about the studium. So professionally, my interactions here at Orléans were very satisfying, and I've continued these interactions with my colleagues here. But I think arguably the thing that was actually most important for us as a family, and my wife Sue was here as well, she was with us. We had our 2 children with us. Our daughter Maggie went to Collège d'Aulnois for the year, and at the end of June, she spoke French like every other 13-year-old kid. And our son Rob came and was at the university for a while studying STAPS. But more importantly, he joined a water polo team in Fleury-les-Aubrais. And he was here actually for 2.5 years. He stayed after we left. And among other things, what I've noticed is that Robert became extremely skilled at giving insults to somebody in French, which is very important. No, he also swears very well in French. But no, but more seriously, I think, as Sue and I were just talking about this the other day, that year in Orléans was transformative for our family. It really changed us in a profound way. And I think that I thank the studium, Paul, and others here for that opportunity. It made a big difference in our family. With that, I'll close. Thank you very much.